Mercury. It's not just the planet closest to the Sun. It's a planet where nothing is alive, where everything is scorched by the Sun's destructive rays. But we still have more to tell about the first planet in the solar system. So what is Mercury like? Hubble. Studying the planet for many years was problematic, and that's despite the fact that only one planet separates Mercury from Earth. To see the planet from Earth, you need to wait for sunset or sunrise. For a long time, it was widely believed that at different times scientists were observing different celestial bodies. Accordingly, Mercury initially had several names. With the development of technology, the situation became much clearer. Over time, researchers also determined the size of Mercury. Its radius reaches 2,440 kilometers. This value is equivalent to almost 40% of the radius of our planet. Thus, Mercury is the smallest planet in the solar system. Even some moons are larger. When assessing the planet's shape, it's worth noting that it's nearly perfect. The difference between the two diameters, polar and equatorial, is less than a kilometer. An interesting feature of the planet is its size. The fact is, considering its dimensions, Mercury is quite massive. 3 times 10 to the 23rd power kilograms. For example, the moons in the solar system, Titan and Ganymede, are larger than Mercury. But at the same time, if you add up the masses of these two moons, the result will be less, the mass of Mercury. The planet has a massive metallic core, which takes up more than half of Mercury's volume. The diameter of the core is about 4,000 kilometers. After the core comes the mantle. It is 400 kilometers thick. Its composition is mainly silicate rocks. Next, Mercury's structure is completed by a crust that ranges from 15 to 37 kilometers thick. Studies of the planet's surface have shown that significant geological processes last occurred there almost 4 billion years ago. A large number of craters have also been observed on Mercury. For many years, scientists used only a telescope to study the planet, and it was very difficult for them because of the huge amount of sunlight surrounding Mercury. The situation improved in the second half of the 20th century. In 1974, the American robotic space probe Mariner 10 was sent to the planet. During its mission, the spacecraft provided images of almost half of Mercury's surface. In addition, scientists were able to learn about the planet's magnetic field and the surface temperature. It turned out that helium predominated in Mercury's atmosphere, and the atmospheric layer itself is quite thin. After Mariner 10, though, it wasn't until August 2004 that the Messenger spacecraft began its mission to study Mercury. The probe reached the planet 11 years after its launch. As a result, we received numerous images that captured almost all areas of Mercury. Thanks to Messenger, we learned that there is a wide variety of landforms on the surface. Mercury's magnetosphere is also interesting. The planet completes a full orbit around the Sun in 88 days. Its orbit is elongated in shape. The minimum distance between Mercury and the Sun is 0.31 astronomical units. At the opposite point, the value increases to 0.47 astronomical units. When Mercury is closest to the Sun, it turns one side and then the other toward the Sun. These areas are called hot meridians because they receive the most sunlight. In the hot meridian, there is an interesting object called the Caloris Basin. It's not called that for nothing because it's the hottest area on the planet. There, the surface temperature is about 427 degrees Celsius. Actually, Caloris Basin is a huge impact crater that covers about 2 Mercuries. Almost 4 billion years ago, a massive asteroid crashed into the planet. The impact deformed a part of Mercury, which at that time was a young protoplanet. The crust had barely had time to solidify, and the collision caused a huge amount of molten lava to erupt to the surface. And even now, on the surface of Mercury, we can observe a bright spot that clearly contrasts with the surrounding area. That's how Caloris Basin was formed. Inside this landform, there are many craters. In the middle of Caloris Basin, there's the Pantheon Fossae. The grooves originate from a single center. Their number reaches 230, and their width ranges from 1 to 8 kilometers. Their lengths vary. Some grooves are about 175 kilometers long, but others are even longer. How exactly the Pantheon Fossae formed is still unknown. Scientists have put forward several theories about this. One of them says that it happened because Mercury cooled down. Another theory is that it happened because of tectonic processes on the planet. There is also a completely opposite region on Mercury, where it is extremely cold. At the poles of the planet, it is always twilight because Mercury's tilt is minimal. Here, at the North Pole, is the Borealis Plain, and this is the coldest region on the planet. The temperature there drops to minus 193 degrees Celsius. There are also areas with water ice here, about 2 meters thick. A layer of dust made of rocky material covers the ice. This prevents evaporation. It is worth noting that the temperature on the highlands in this area, that is, in places where at least some sunlight reaches, can reach up to 107 degrees Celsius. Even if some areas are adjacent to each other, there can still be a significant temperature contrast between them. If you move south, you can find the ring-shaped Rachmaninoff impact crater, one of the largest on the planet. The object is about 1 billion years old and has a diameter of about 290 kilometers. Rachmaninoff most likely formed as a result of volcanic activity, since the rocks here have a reddish tint, unlike other areas of the planet. Traces of solidified lava flows have also been found in the crater. The Rachmaninoff crater also contains the lowest point on Mercury. Its value is minus 5,380 meters relative to the average level. Even further south lies the massive jagged Enterprise Scarp. It is more than 800 kilometers long. The scarp runs from the northeast to the southwest. Enterprise is the largest scarp on Mercury. It is believed that the formation of such a landform was caused by a decrease in temperatures inside Mercury. As the cooling process occurred, the planet shrank slightly, which caused folds to form on its surface. Approximately 50 Enterprises would fit in the area of the Rembrandt crater, the largest on Mercury. The diameter of this formation reaches 716 kilometers. Inside the crater, there are many smaller objects. At the very bottom of the Rembrandt crater, cracks were discovered that together resemble a spider web. From the center to the outer ring, mountain ridges stretch out, each about 180 kilometers long. Data about such landforms in the crater make it easier to study the processes occurring inside Mercury. Over the years, we have obtained a huge amount of information about Mercury and the objects on its surface. However, we cannot put this matter to rest, and there are still many unresolved questions. That is why Mercury is awaiting another grand mission. The Bepi Colombo robotic probe, developed by the European Space Agency and the Japan Aerospace Exploration Agency, is already on its way to Mercury. Thanks to this mission, we will be able to expand our knowledge about the planet's surface features, its atmosphere, magnetosphere, and solar winds. It is expected that Bepi Colombo will be able to enter Mercury's orbit as early as 2025. Currently, technology does not allow us to create a spacecraft that could, for example, operate directly on the planet's surface. After all, Mercury is, to put it mildly, a harsh place. However, space science has proven more than once that it can achieve the impossible, and we will surely make progress on this issue over time. Surely, you have wondered at least once about what lies beyond the universe. What shapes could it possibly have? This also interests scientists who have been trying for decades to understand the nature of the cosmos as a whole. And the main questions are, can we consider the universe to be infinite? Or is there a place that we can consider its boundary? If it is not infinite, then what shape does it have? Let's now focus on the last question about the supposed shape of the universe. The most obvious answer might seem to be a sphere, since spherical objects are common in the universe. However, can it itself have the same shape? The part of the universe that we can see may vaguely resemble a sphere, with our planet located at its center. But such a picture does not show the real state of things, since we are only able to observe those parts of the universe whose light has reached the Earth. The light from other objects is still on its way. That's why we don't see them. In that case, the radius of the observable universe would be about 13.8 billion light years, since 13.8 billion years have passed since the Big Bang. And it is exactly during this period that the light from the observable part of the universe has reached the Earth. However, it's not that simple, and the radius is actually larger. The universe is expanding. Some objects are slowly moving away from Earth, so the observable universe's diameter will be about 93 billion light years. This makes us realize that there is something beyond the visible part of the universe. That makes it very hard to determine the true shape of the cosmos. Thanks to the general theory of relativity, scientists have concluded that there can be curvature in space-time due to mass. The curvature of space occurs around various cosmic objects, causing the orbits of other nearby objects to also become curved. The curvature of vast regions of space occurs under the influence of the universe's energy and the mass of matter. Despite the fact that there are many different objects in the universe, overall we see it as a homogeneous space. Accordingly, there must be some average curvature. The factors that can also influence the shape of the universe are the force of gravity and the expansion of space. These forces seem to be in a struggle with each other, since one force of gravity tries to compress the universe, while the other does the opposite, expand it. Which force will prevail determines the shape of the universe. To determine the rate of expansion, the Hubble constant is used. According to the latest calculations as of 2022, is about 73 kilometers per second per megaparsec, give or take 1. The strength of gravity is determined by the mass of energy and matter in the universe. However, we don't know the size of the universe, and accordingly, we don't know what these values will be. In order to find out the shape of the universe and the curvature of space, the value of the critical density was determined. The critical density is the average value of the density of energy and matter in the universe. This indicator can contribute to a certain balance between the force of gravity and the expansion of the universe. In this case, neither force will prevail over the other. If we compare the two densities, the critical and the actual, we have a chance to find out what shape the universe has and how it may develop in the future. It is worth noting that, according to the general theory of relativity, from the point of view of geometry, there are 3 possible shapes for cosmic space, so to speak. It's important to remember, if the critical density is greater than the actual density, the expansion of the universe will continue indefinitely, and the force of gravity will not be enough to stop this process. In this case, the shape of the universe will be highly curved. Such a space is called an open universe with negative curvature. If the situation is the opposite, that is, the actual density exceeds the critical density, the expansion process will stop after some time, and the process will reverse due to the prevailing force of gravity. You could say a reverse Big Bang will occur. In this case, the shape of the universe will be spherical. This is a closed universe with positive curvature. Even though it is finite, it has no boundaries. Just so you understand what we're talking about, if you move in one direction in such a space, after some time you'll end up at the point where you started your journey. For a long time, it was believed that this version was as close to reality as possible. It could also be that both the actual and the critical densities are equal. In this case, the expansion of space will happen more and more slowly, and this can last forever. The shape of such a universe would be flat, without a definite end. In a flat universe, you can equate the force of gravity with the expansion of space. And scientists have discovered that this is exactly the kind of universe we live in. Based on numerous calculations and studies, our universe is flat or as close to flat as possible. However, remember that we are talking about three-dimensional space, while the shape of planets is close to spherical, and space itself is homogeneous and infinite on a large scale. To find this out, scientists calculated the density of matter in the universe. Since the size of the universe was unknown to us, it was impossible to calculate the density of all space. However, we mentioned the uniformity of the cosmos, which means we could take a certain region and determine only its density. This would also be the density for the universe as a whole. To calculate the density, we need to know the volume and the mass. Mass is more complicated because we also have to take into account what we can't see with our instruments. The matter of the universe is not just galaxies. About 27% of all the mass is dark matter. Thanks to its gravitational influence, galaxies continue to exist as a whole and do not fall apart. 68% of the mass of the universe is dark energy, which has the opposite effect. It contributes to the separation of structures, and therefore to the accelerated expansion of space. At the same time, knowing the value of dark energy is important in order to determine the mass of the universe. And let us remind you, if we know the mass of the universe, then we can also find out its density. It's important to determine what the mass of galaxy clusters is. One way to find out the speed of the components of a galaxy cluster. Knowing this value, you can also determine the mass. Note that this is not the only option. You can use gravitational lensing. The mass of the galaxy cluster determines how much the light coming from the galaxies is bent. By knowing the degree of bending, you can determine the mass of the universe. As a result, the researchers concluded that the actual density is about 70% less than the critical density. However, the thing is that this value includes both dark matter and ordinary matter. But if we add dark energy to all of this, then the actual and critical densities will be more or less equal. Accordingly, in the end, we get a flat universe. But there's another way. Just determine the value of curvature. As you know, in two-dimensional space, the sum of the angles of a triangle is 180 degrees. But if you draw a triangle on a positively curved surface, the sum of all the angles will be greater than 180 degrees. And if we take a negatively curved surface, then the sum is already less than 180. It turns out that if we know the sum of the angles, we can determine whether the curvature is positive or negative. And that's roughly what researchers do. We can speculate a lot about what shape the universe has. But if we're dealing with flat space, then how will the cosmos evolve in the future? So what does that mean? Will dark energy decide this? After all, it acts like anti-gravity for the universe. If dark energy prevails, then the expansion of space will be endless, forever, and at an ever-increasing rate. Then, sooner or later, the distance between galaxies will increase many times over. And then, with the last star extinguished, the universe will become absolutely dark and cold. Of course, that's assuming the nature of dark energy is as we assume. Even if the universe is geometrically flat, we can assume that the topology might be inhomogeneous. We might even end up concluding that the universe actually has boundaries. Anything is possible. After all, there is still so much we don't know. And what shape do you think our universe really is? On our Hubble channel, for the most part, we focus exclusively on real scientific discoveries in space. But this is one of those cases when we need to turn to science fiction. Yes, it's fiction, where you can't take everything at face value. However, thanks to books of this genre, it's possible to get a wide audience interested in science. Sometimes science fiction literally predicts the future. Sometimes it depicts our world in a parallel reality where everything has its own distinctive features. If you were asked to name a science fiction writer, who would be the first to come to your mind? Most likely Isaac Asimov, who made an invaluable contribution to this genre. Throughout his life, Asimov wrote more than 280 popular science articles and books. Asimov's plots are truly impressive not only for their unexpected twists, but also for their incredible accuracy. The writer actually predicted the emergence of many technologies, including wireless devices, mobile phones, and more. Who knows, maybe some of his predictions that haven't come true yet might be realized soon. Today we're going to talk about one of the most famous novels by Isaac Asimov. Before we start discussing the plot, let's go over some important facts. There are 4 fundamental forces in the universe. These are the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. Gravitational forces play a key role in the formation of stars. The existence of planetary systems depends on this. It seems that we don't feel gravity, but it directly affects us. Without it, we would simply float in the air. The gravitational force is characterized by the exchange of graviton quanta. Electromagnetic forces enable atoms to function and also account for friction, resistance, and elasticity. An important point is that electromagnetic interaction helps solid bodies hold together in a certain shape. The weak nuclear force causes the decay of particles, which leads to the transformation of some subatomic particles into other subatomic particles. For example, through the exchange of the Higgs boson, when a neutrino deviates from a neutron, this leads to the transformation of the neutrino into an electron and the neutron into a proton. The strong nuclear force is the strongest of the 4 fundamental forces. It is thanks to it that atomic nuclei remain stable and continue to exist. Thanks to these 4 forces, the process of particle exchange occurs. These fundamental forces make the world around us the way we know it. The fundamental constants also depend on them. We're talking about the gravitational constant, Planck's constant, the mass of elementary particles, the speed of light, and more. Fundamental constants are the foundation of everything. If you change even one of the components even slightly, the entire order of the universe will change drastically. The properties of the fundamental forces will also be different. This could be called a parallel world. In such a world, the nuclear interaction could be an order of magnitude stronger than in ours. And what could this lead to?
To answer it, we can look at how Isaac Asimov presented it to us. The writer describes in his novel how the characters deal with the consequences of enhanced nuclear interaction. What comes to the forefront here is the theory that there may be a huge number of parallel worlds in which the strength of the strong nuclear interaction differs. In some cases, it is higher, and in some even lower than in the real universe. Asimov argues with the statement made by some philosophers like Friedrich Schiller that even higher powers are not able to solve the foolishness of humanity. The writer emphasizes that human foolishness does exist. However, people themselves are not stupid, even though they notice only what fits into their worldview and resist anything that is outside their perspective. The first part of the novel shows how the conflict arises between personal desires and the consequences, which can be destructive. The work also explores the main theories in nuclear physics, including the one that states the properties of energy are directly related to the properties of a particular universe. Intriguing? The characters in the novel have obtained a cost-free source of energy and don't want to understand what negative consequences this might have. Everything is further complicated by the existence of studies that point to a positive effect. There's also the issue that science can be influenced by those who have authority and power. It's easy to manipulate facts. You can create conditions so that the results of a study turn out the way someone specific wants them to. So, the inhabitants of the parallel universe in the novel gained the ability to exchange matter between universes. Asimov called it the inter-universal electron pump. But with such a process, the nuclear interaction intensifies, which means there is a threat of the sun exploding in our universe. For the parallel universe, this is a positive thing because it's an endless source of energy for them. In the parallel world, there are peculiar inhabitants: emotionals, rationals, and pistons. Emotionals were more associated with the feminine, while rationals were associated with the masculine. For emotionals, emotions were always a priority, and intellectual abilities were not valued. Thus, one of the heroines who belonged to this gender was condemned for her intelligence and constant curiosity. Let's talk about the third part of the novel. It describes what happens on the moon. Asimov describes the hostility of the moon's inhabitants toward Earthlings, their arrogance, desire for independence, and artificial food products. Probably, the author wanted to show what our life would look like with further technological development. And it was on the moon that the heroes of the novel planned to place special devices that could neutralize the destructive effect of the pump on our universe. Isaac Asimov's novel is fast-paced and eventful. You definitely won't be bored. And at the same time, you'll get plenty of scientific discussion that will make you think about universes, including parallel ones. If you couldn't stand physics in your school years, then the novel The Gods Themselves, like many other works by Asimov, will help you develop an interest in this science. On top of all that, there's also a reflection on humanity's mistakes and its inability to admit them, about the psychology of human cognition and more. So it turns out to be an interesting mix of psychology and science. There's something interesting for everyone in this novel. And we definitely should think about whether parallel worlds with completely opposite fundamental physical constants can exist. Many things described in science fiction works have been found in reality, so who knows, maybe it's the same situation here, and Asimov's book will point scientists towards solving this question. And what do you think? Will we ever learn about parallel universes? And will they be similar to the one described by Asimov?
The past of humanity amazes with its capabilities and proves that nothing is impossible for it. It's interesting to know that at the bottom of the ocean and beyond Earth's atmosphere, we will create special research devices. There's little space left on our home planet, but we can create artificial islands. And what could we do if the population suddenly reached such a limit that it became too crowded for all of us on Earth? Of course, we can look for planets with optimal living conditions in other galaxies, and that seems like the most obvious option. But what if we create our own planets in the habitable zone of our system? This might seem a bit too fantastic to you, but science does have something to say about it. So what would such a system with multiple planets look like? How many objects can it contain? Is it possible for more than one planet to be on the same orbit? And can all the components of such a system orbit around a single star? Before we move on to discussing our ideal system with many planets, let's say a few words about the current situation with the solar system. While we know of a huge number of planets outside the solar system, currently about 5,000, there are 8 planets in the solar system itself, and it's worth noting that our system holds the record for the number of planets in it. We know about the TRAPPIST-1 system, which has 7 planets, and the solar system shares its record with Kepler-90, which also has 8 planets. These systems share other characteristics too. The more massive planets are farther from the main star, while the smaller ones are closer. Also, the host stars are sun-like. However, there is one important difference. In the Kepler-90 system, all the planets are within 1 astronomical unit from their star. That means even Earth is farther from the Sun than these planets are from their star, and Earth is the 3rd planet out of 8. From all this, we can conclude that the density in the Kepler-90 system is an order of magnitude higher. That means it's possible to create a situation where the distance between the planets is less than in the solar system. Next, it's important to understand whether there is anywhere in the universe a system where there can be more than 1 planet in the habitable zone. In our planetary system, we have Earth, the only planet with optimal conditions for life. In the early stages of the solar system's development, Venus and Mars could also have been suitable for life, as they are close to the habitable zone or even within it. We can take the previously mentioned TRAPPIST-1 system as an example. Its habitable zone contains 3 planets. Scientists suggest that there are systems with even 7 planets in the habitable zone. What about having several planets on the same orbit? Here, we don't even have to limit ourselves to just 2 planets. There could be more. It's worth noting here that the 2 Lagrange points L4 and L5 are highly stable. In the Sun-Jupiter system, there are Trojan asteroids at the Lagrange points. They are located at approximately equal distances from the Sun and Jupiter. In theory, not only Trojan asteroids can exist, but also Trojan planets, whose locations can almost coincide with the mentioned points. At the same time, such planets have not yet been discovered in the universe. We talked about planets that can form naturally in the universe, but we will talk about creating systems with the maximum possible number of planets. We can rely on the work of the astrophysicist from the Bordeaux Observatory, Sean Raymond. In his articles on the topic we're interested in, he used the results of real research, even though his work is not peer-reviewed and not published in scientific journals. We will take some of the information we need from there. We know that the density of systems similar to the solar system can be an order of magnitude higher, but what will determine the maximum density value? For further discussion, we will often use the term Hill sphere or Hill radius. This is the space around a celestial body where its gravitational influence dominates. That is, this space determines the orbits of less massive bodies, despite the influence of a larger object around which the body itself directly revolves. The Hill sphere is located between the L1 and L2 Lagrange points. Earth's Hill sphere extends to 1.5 million kilometers. Since the Moon is almost 400,000 kilometers away from its planet, we can conclude that Earth's satellite is located within the Hill sphere. Also, 1.5 million kilometers is equal to the distance to the Lagrange points L1 and L2. As we can see, the Hill sphere we get is quite large. All 8 planets can fit inside it. However, at what distance between the planets will the system be stable? The interaction between the planets increases if one enters the Hill sphere of another. Accordingly, destructive processes such as collisions can occur between 2 objects. In the articles by the aforementioned Sean Raymond, studies are mentioned which state that the distance between planets should be equivalent to 5 to 10 Hill spheres. And here the question arises. In theory, how many planets could fit in the habitable zone of our solar system? It should be noted that we don't know its exact size. The habitable zone extends from 0.95 to 1.37 astronomical units from the Sun. Sean Raymond, taking these calculations into account, concluded that we could fit 6 planets capable of supporting life within the habitable zone of our planetary system. So what can we do to increase the number of these planets? It would be nice to place at least 2 planets on the same orbit, so that one of them is located at one of the Lagrange points, L4 or L5. This way, we would already have 12 planets, and the system would still remain stable. Let's move on. How can we increase the number even more? Based on materials from the journal Celestial Mechanics and Dynamical Astronomy, we conclude that there can be more than 2 planets with equal masses on the same orbit, provided that they are equally spaced and at least 12 Hill radii apart. The minimum number of planets on a single orbit can reach 7, and on Earth's orbit, in this scenario, there could be as many as 42 planets. As we recall, there can be 6 orbits in the habitable zone of the solar system. But is it possible to have that many planets on each orbit? The mass of the planets does not have a significant effect on the distance between the orbits. Accordingly, if we placed 42 planets on 6 orbits, then in total we would have 252 planets with optimal conditions for life. How far apart the orbits are depends mostly on a single planet, but specifically the one that influences the planet from another orbit. Let's go even further and try to increase the number of planets even more. If we're going to do it, let's go all the way, as they say. Here we need retrograde orbits. In the solar system, the planets move along their orbits in the same direction. If the distance between the planets is relatively small, then the planets on different orbits affect each other gravitationally, which leads to instability. If the planets stay close to each other for such a long time, the consequences will be serious. In this case, it's better to isolate the 2 planets from each other so that they spend less time close together. How can this be done? We need these 2 bodies to move along their orbits in different directions. That is, retrograde motion will occur. This way, we will not only reduce the gravitational influence of some planets on others, but we will also be able to decrease the distance between the orbits. Since we're already raising the stakes like this, habitable planets could form outside the habitable zone. We'll set a limit of 1,000 astronomical units, again based on the work of Sean Raymond. This is the optimal distance from the main star, since external influences on the planets won't be significant. Thus, we can fit 57 rings into this zone, each with 42 habitable planets. In total, that makes 2,394 objects. Even though such a number may seem incredible and extraordinary, in this case, the total mass of all the planets still wouldn't outweigh the central star. The Sun will still be an order of magnitude more massive than all the objects in the system. Yes, right now, our ideas are fantastical and purely theoretical. Of course, in our solar system, something like this simply cannot form. However, over time, we may discover planetary systems similar to the ones we've described. And what do you think? Are such discoveries awaiting us in the future? And how soon?